Alright, today I'm going to be explaining the photoelectric equation. First things first, the energy of a photon and how to calculate it. Basically, it's a really simple equation. All it is, if I could write, all it is E, which is energy, equals h v. And that h stands for Planck's constant, which is 6.626 times 10 to the power of negative 34 joules seconds. This V is just frequency, which is per second. And then energy is in joules. Okay, simple enough, nothing too complicated. Now, what is the actual photoelectric equation? Again, nothing complicated. I like to write it this way. There's multiple ways how to write it, and I'll show you later, but this is how I write it. I do kinetic energy of a photon, which a photon can be an electron, equals hv, the energy of a photon, minus the work function. And the work function, it can be in, like, I don't really know how to explain it. All I know is the electron voltage, it can be written in electron voltage, and 1 electron voltage equals 1.6 times 10 to the power of negative 19 joules. Okay, so you might have to convert this to electron voltage, or from electron voltage to another different conversion. But yeah, really simple. And this, I said it earlier, kinetic energy equals the energy of the photon minus the work function. Simple. Nothing too complicated. Alright, what is work function? Simple definition is work function is the threshold of energy that you need to get or get over in order to release a photon from the metal surface. Okay? So basically, when the photon's energy is greater than the work function, part of the photon's energy is used up in the freeing of the electron from the metal surface. Any remaining energy received by the electron from the photon turns into kinetic energy. Okay? And I'm going to write down some easy things that you should all know. So, when the energy of the photon is less than the work function, what happens? No electrons are ejected. Okay? So if we can't get over that hump, over the threshold, okay, no electrons, there will be no kinetic energy given to the electrons. Okay? Now when the energy of the photon is greater than the work function, electrons will be ejected. Okay, so again, when we get over that hump, if we have enough energy to get over that hump, kinetic energy will be given to the electrons. They'll get shot out at some sort of speed. And finally, when the energy of the photon equals the work function, electrons are ejected. What do you guys think the kinetic energy of the electrons are when the energy of the photon equals the work function? What do you think? Pause the video and just say it out loud. Okay. Kinetic energy of the electron will be equal to 0. Okay? Because there is no remaining energy to give to the electrons, so they have nothing to to absorb, so they're at 0. Okay, here's a pretty simple problem. A metal has a work function equal to 4.65 times 10 to the power of 19. So the work function equals 4.65 times 10 to the power of negative 19 joules. If a violet photon, okay, so violet we know will be, it'll have a lower, a higher frequency and a lower wavelength. So 405 nanometers, that's the wavelength, small wavelength. So we know the wavelength equals 405 nanometers. Do not forget the nanometers. Do not forget what it is. Impacts the metal surface in a vacuum. Will an electron be ejected? Okay. So we know that the energy of a photon equals hv. Okay? And we know that the frequency equals the speed of light over wavelength. Okay? Because we don't have wavelength directly in the equation. However, we can convert frequency to speed of light over wavelength in order to, successfully solve this equation. So we're looking for, will an electron be ejected? Okay, so we just have to see if it gets over that threshold. We don't need to really know what the kinetic energy will be. However, we need to know if the energy of the photon is greater than the work function. And the work function is right there. So all we really have to do is just plug in all the constants. So Planck's constant, 34, times the speed of light, which is 3 times 10 to the power of 8, over, and then we have to do 405 nanometers, and we have to multiply that by 10 to the power of negative 9. Okay? And then once we get that, final answer should be, I have it right here with me because last time I was doing the calculations with you guys, decided this might be easier. Final answer should be 4.908 times 10 to the power of negative 19 joules. And as you can see, and we're just going to say 4.91. 4.91 is greater than 4.65, and we can just say it. We don't have to say times 2 to the power of 19 or negative 19 because they're both that. So we know we don't really have to compare that part. However, this aspect we do. So 4.91 is greater than 4.65, so we can say yes, an electron will be ejected. Boom. Simple. Okay, the second question is a little harder. However, it's really not that complicated once you get into it. So, what is the kinetic energy? So we're looking for kinetic energy of the photoelectron that is produced when a blue photon with a wavelength of 475 nanometers strikes a potassium surface in a vacuum. The work function for potassium is 2.43 times 10 to the power of negative 19 joules. Okay. Again, not that complicated. Just have to do work function equals 2.43 times 10 to the power of negative 19 joules. Okay, so we have our work function, and we see that it has a wavelength. And we're just going to really have to do what we did with the last question. However, there's one extra step, and it's such a simple step. So, again, wavelength equals 475 nanometers. And we're just going to let's just write out the equation. So, kinetic energy, electron equals, boom, minus work function. Okay. So we're looking for kinetic energy, so we have nothing to plug into there. We do have the Planck's constant. We do have frequency because we just put speed of light over wavelength, and then we do have the work function. So really all we have to do is just plug this in. So we're going to do 6.626 times 10 to the power of negative 34. And then, I mean, I'm not going to write the units, however, Planck's constant is joules times second. But so that times, we're just going to do speed of light. So 3 times 10 to the power of 8, and then over 475 times 10 to the power of negative 9. Okay, so pause the video and let me know what you get. Okay, you should get 4.184 times 10 to the power of negative 19 joules. Okay, that is what you should get. Now, that's just step one. Let me just step one. Okay, step two. If you've been through the 3rd grade, you should know how to do this. It's just getting 4.184, the energy of a photon, times 10 to the power of negative 19, and subtracting that by the work function, 2.43 times 10 to the power of negative 19. Okay, and once you get that, again, pause the video. Shouldn't take you more than 15-20 seconds at max, and you should get 1.755 times 10 to the power of negative 19, and then joules. Okay, it's that simple. It's really not that complicated. It's just a couple of steps, and you guys will do great.